Okay, welcome back, mechanics students, AP Mechanics students, to Differential Equations 3, the last lesson in the Differential Equations unit, and as it turns out, the last lesson of new information for the entire course. So here we are, pat on the back, you've made it, and this is it, okay? I forgot to mention this at the end of the last video. The last notes were probably extremely intimidating, or might have been, maybe not, maybe you enjoyed them and you understood them. But if you feel like, oh man, that's a lot to go to do in a problem, keep in mind the format of the AP test. This is out of the question for multiple choice. Maybe they might ask a few concepts about differential equations on a multiple choice, but those questions have to be solved in 1.2 minutes or 1.25 minutes, whatever it is. They have to be like problems that can be done in a minute. Otherwise, they're not fair questions. The AP would not put a question like that in a multiple choice. Free response questions are limited to 15 minutes. So if you look at the notes in all those solutions, they were very long. There's no way that you have to know all of that in a differential equation problem. You'll find when you do the actual free response problems, they may ask only one part, maybe like case 2A, solve for the velocity, and that's it. And the rest is concepts or sketching graphs. So you're not going to have to churn out all those long solutions like that. Okay, that's way too much to fit into a 15-minute time slot question. But any one part might show up. Okay, the most common things are solving for the velocity. So if you feel overwhelmed, look back at all the cases and just go as far as studying how to get the velocity. Okay, and like I say all the time, the AP test, you don't have to get everything right. If you get 68% of the tests correct, you get a 5 out of 5. So any parts that you can get, just concentrate on getting as much as you can, and don't stress out about not being able to solve everything in the notes. Okay, it's not going to hurt you if you can't do it all. All right, that being said, we are doing two more cases, case 3A and 3B. And they're like 2A and 2B. The difference is that the velocity, the force of air resistance is minus kV squared instead of kV. This is actually a more accurate model of air resistance. It actually is proportional more often to velocity squared than velocity to the 1 power. So this is actually, again, more like what car experiences with air resistance. So the first case, we have an object projected forward and then let go. So there's no more forward force. It's coasting, but it's coasting against the air resistance. Force diagram, gravity and normal force balance. That's the earth pulling down. That's the road surface holding the object up. And then the air resistance backwards, kV squared. You could put a minus sign there. It doesn't matter. I already have the minus sign included with an arrow in the backwards direction. Put it in or not put it in. You're not going to lose points for that. Okay, so there it is, the force diagram, and we want to find the velocity as a function of time as this thing slows down because of air resistance. Can you remember the 4 steps of solving a differential equation? Pause and briefly say them in your mind. Okay, so hopefully you remembered what those 4 steps are. If you didn't, well, here they are, maybe one final time. So the first thing we do is we create a differential equation. Step 1, create a differential equation using Newton's second law, A equals F net over m, and realizing that A is actually the derivative of velocity with respect to time. If you look back at the force diagram, the only force is the backwards kV squared. That's the only force that produces an acceleration. The minus sign here is critical because it is in the backwards direction. If you left it off and left positive, this would be something speeding up by air resistance. It doesn't make sense. And divided by mass. So we made differential equation with Newton's second law, step 1. Step 2, we separate the variables. Okay, how do we do that? Well, we've got dv over here. We want to have all velocity on this side, all times on this side. So we can divide this v squared over to this side and have dv over v squared, which I write v to the minus 2 power because it's going to help me set me up to integrate. So I divide it by v squared, I move the dt to this side, and I have negative k over m times dt. And then I integrate both sides. That's step 3, integrate both sides. Remember, this didn't start at rest. It's something that's projected forward, and it's going to slow down by air resistance. So this is what you projected it forward with. What's its velocity later as it's slowing down? That's what we're looking for, v0 to v final. The timer begins at the moment you launch the thing, and then at some later time we want to know what the velocity is. So now we have to integrate both sides. We do that by using a simple power rule. We add 1 to the exponent, negative 2 becomes to the negative 1 power, and then we divide by that new exponent. And then we have our limits, of course. And then on this side, we integrate dt, which is again a trivial integral just to t, from 0 to t final. And we have still the negative k over m. Now what we have to do is plug in the limits and solve. That's the fourth and final step in solving these differential equations. So I put the negative to the other side and made it positive. So that's why there's no more minus here. And I just do 1 over vf minus 1 over v0. And on this side, kt over m. Oh, I forgot the f, kt final, minus 0. It's not critical if you don't put the tf, by the way. That's fine if you just leave it that way. So I move the v0 to the other side, 1 over v0. And then now what I have to do is solve for v final, not 1 over v final. So what I have to do is do the reciprocal of both sides. First, I have to find a common denominator here before I could flip it over as a fraction. So if I multiply this fraction top and bottom by v0, and this top and bottom by m, I have a common denominator of mv0. So my combined top is ktv0, and over here m. And the bottom is mv0, that's the common denominator. So now I'm going to flip that over and I have my final answer for final velocity. Notice it follows the pattern. We projected this at v0. Remember, that's the case 3a. We projected this forward at v0, and then it's going to slow down by air resistance. So what we should see is a function that starts at v0 and goes to 0. And that's what we see. If you plug in t equals 0 here, that makes this whole term here 0. And we have mv0 over m, which is just v0. So that's what the function starts at. Then as time gets bigger, this denominator gets bigger and bigger. As time goes to infinity, the denominator goes to infinity. And so we're dividing by an ever bigger number. We go to 0 velocity in the end. So that's the velocity function. The next thing we're going to do is solve for how far this thing goes. And the way we do that is, again, we follow the 4 steps. Again, I'm like a broken record. Can you say them in your mind? Pause the video and say them, practice saying them. So the first step is you make a differential equation by realizing that this velocity here is actually a derivative of x. And we just bring the function here, okay? So now the step 2 is we have to separate these variables. We're going to move the dt to this other side, and then we'll have all time and constants on this side and only x on that side. So let's do that. Okay. Let's see. All right. Yeah, looks maybe a little higher. So now that I separate the variables, I can integrate both sides. I integrate from 0 to x final and 0 to t final. So this side, trivial integral, right? dx to x. This side, however, it's a natural log function. We have dt on the top, and by the way, mv0 we could separate away. But we have dt over this entire thing here. So we have dt over t essentially, which integrates to the log of all of this. But once again, that would be the answer. If we had dt over t, it would just be log of t. But because we have this function, we've got to divide by the derivative of what's inside here, which is kv0. We divide by that. Once again, you could show that with a U substitution. Once again, the notes are way too long already, so we don't want to go through with a U substitution. If you just want to remember that you divide by the derivative of what's inside, boom, you've got it. So then plug in our limits and solve. That's the fourth step. After we integrate, we plug in our limits, x final. And then we have just touching this up, the v zeros go away, m over k. We plug in t final into our log, which is there, and we plug in 0 into the log. Remember, as I said in the previous video, plugging in 0 into this log doesn't mean that you have 0 there. You have 0 for time, which makes it log of just m minus 0, or m plus 0, which is log of m. And then you could combine those into one log, and you have the final answer. The last thing we're going to do with this case is just graph these. So the x function, if you remember, if you look back in your notes, it's the natural log function. Oh, I got it right here, right? So natural log. Natural log looks like the 1 minus exponential, but it actually never peaks. So this never stops. In theory, it goes forever in the forward direction. Okay, that's the log. It just sort of keeps stretching that way, but still keeps rising. The velocity function, I have it covered up, but it starts at v0 and goes down. This is not the exponential. It's not an exponential. It's a reciprocal function. If you go back at the function, you'll see that. Okay, so that is case 3a. Halfway through, right? So a lot more to go. Actually, it turns out not really. Fortunately, there's a little gift that we get from the AP curriculum in this one, so I don't need to cover. So case 3b. Recall that case 3a was when you projected something forward and then let it go, and then only air resistance was stopping it. In this case, this is like, again, the car. You floor the gas pedal, and you get that forward force of the engine, and then air resistance back in the backwards direction, kV squared instead of kV like we had in case 2b from yesterday's notes. And gravity and normal force balancing. So what we're going to do is first generate the acceleration as a function of time using Newton's second law. A is F net over m. And A is the derivative velocity with respect to time. If you look back at the force diagram, we have a forward force F, backward force kV squared. So there is the differential equation. Okay. Before we go ahead and we solve that differential equation for velocity as a function of time, the first thing we're going to do is a little something different now. We're going to first just solve for what we call the terminal velocity, or the top speed of this car. Okay, so the way we do that is we realize the thing reaches its top speed when it no longer accelerates. So we plug in 0 for the acceleration and v terminal for the velocity, and we solve for v terminal just with algebra. We multiply the m to the other side, so it's gone. We add the kv squared to this side, divide by k, take the square root. There's the terminal velocity. Once again, it does not depend on the mass of the car. All it depends is on the engine force, the strength of the engine, divided by the air resistance coefficient. So more aerodynamic, that would mean that's a smaller k value, faster the car can go. So there's the terminal velocity. Plug in 0 for the acceleration and solve for v. The next thing, what is the velocity as a function of time? Here's the little gift we get. That's not part of the curriculum. We would, if you remember, have to take the differential equation, separate their variables, integrate both sides, and solve it for velocity. The reason why that's not in the curriculum is because it involves hyperbolic functions, which are not included. So you don't have to be able to do that. All you have to be able to do for case 3b is to do a force diagram, write the differential equation, and solve for terminal velocity. By the way, very often in these problems, the problem is for dropping something with air resistance. And if you skydive, you might recall that you eventually reach terminal velocity And the more you fall, your velocity does not increase anymore. And so we would be using this instead of F here, we would have mg, the weight of the thing pulling down, minus the air resistance in the backwards direction over the mass. And then you would do the same thing, find the terminal velocity, but you would not solve for velocity as a function of time. So there it is, the third and final differential equation notes. And the final notes of the entire course, well, we'll have notes when we review, we'll be reviewing stuff, but you have completed AP Physics Mechanics. So if we were in class, I would ask you to give yourselves a round of applause, because it is a tremendous milestone. You have gone through a lot. You've learned a lot of calculus. You've learned a lot, and you see in this differential equations some real heavy stuff you're solving. That being said, also I made some general comments about how you won't have to do all of these problems in one problem. So that's certainly true. The other thing that's a little benefit of these very long, difficult problems is there's not much variation that they could do on you. So if you just sort of go back and memorize how to solve these, the last 2 days of notes, and even maybe just the velocity, you could memorize it, and there isn't too much they could throw at you, and you could probably do just fine. So that's a nice thing too, that there will not be much variation. All right, thanks again, and we will finish with differential equations at the end of this week, and then move on to review next week.